and you have to have volume. And all it is a ratio. All it is a ratio between some mass up here and some volume down below. So density depends upon your units. And most of the units that we use in here would be dealing with grams. And down below we would have centimeters cubed or milliliters. They are the same thing. You say, well, how are they the same thing? Well, centimeter cubed is more like taking a block and measuring the length and width and height of it. And then once you get that, you just multiply those out and you get centimeters cubed. If you have volume, then it's probably going to be measured in a graduated cylinder. And when you do graduated cylinder, a lot of times it's in milliliters, and you got a liquid in there that you would measure, and that would be when you have a liquid or a gas. It could be a gas too. Gas is probably pretty tough on a graduated cylinder. That's a little bit tougher substance in which to do things. So density is a mass over a volume. All it is a ratio. So if I've got a density of 10 grams per milliliter, that tells me that for every 1 milliliter, I have 10 grams of the substance. Okay? So all it tells me is it says, if I have this amount, then this is how much I'm going to have in the other substance. So milliliters go on bottom, and so milliliters will always be 1. So this unit that is on bottom is always 1. So if I set up a ratio, this would be the ratio, 10 grams over 1. Okay. I could also set up the ratio like this, and it would be 1 milliliter for every 10 grams. Well, that's not density, because density is mass over volume. They could have came up with density and made it volume over mass. It's still a ratio. Okay, and so they decided to take the unit of a gram and over a milliliter, and that's how they come up with a property of the ratio. That's all it is, the ratio. So units are really important. You guys pay attention to units. You'll find out chemistry, you have to really be conscientious and focused on unit when you take a look at doing problems, because the units won't lie to you, especially when you're given the information. Remember I said you got background information that you're given? So if you look on the page with some of the different densities, you got the first column that's solids, and you got a variety of different solids on there. If you look at the second column, those are liquids on the table. And when you look at the last column, that's column of gases. So what are some things that you see different in the heading as you go across? What are some differences in the heading that you have to pay attention to? Yep.
The gases are at 0 degrees Celsius and moisture at 25 degrees Celsius.
Yep. So the reason they use 25 is that room temperature is 25 degrees Celsius. So 77 degrees is about room temperature, you know. In here today, it's probably in the 70s. So they always look at natural state of a room temperature, and that's kind of like, that would be what they use. The gases, they just use 0 degrees Celsius because a lot of times with gases we use that as a standard. Later on you'll kind of see that in gas laws. Okay? Questions? Okay. What else is different? Yeah. So which one's grams per liter? So gases are grams per liter because they take up a lot more space, and we want to show digits that are not 0.0000 whatever. They want to show it as a more representation where they don't have a lot of zeros. So it does look like gases are similar densities as the liquids on the left side. They're not. There's about 1,000 times difference in the two. So for example, you can look at a number that's similar. Let's say we take a look at gasoline. Gasoline's 0.74 grams per milliliter. When we look at methane, it's 0.714. You would say, well, they have about the same density. They're not even close. Because the units of measurement is grams per liter in one, and the other, which means taking up a lot more space, 1,000 times the space. So methane gas, which is natural gas, is 1/1000th the density of gasoline. Okay? So, really important for you guys to pay attention to your units. One thing that we really talk a lot about is water. And water has a density of 1 gram per centimeter cubed or milliliter. Those are interchangeable. Okay? They mean the same thing. If I say a milliliter, it comes out the same as 1 centimeter cubed. Alright, so when you think back to the lab experiment you did with the hot water and cold water, which one was more dense? Cold water. So, what am I not giving you that differentiates those two from one another? I'm saying water, in general, has a density of 1 gram per centimeter cubed. Now, you say, well, it has to be at 25 degrees Celsius. But in general, we take water at most all temperatures is 1 gram per centimeter cubed. So, what do you think you'd have to do to differentiate between waters at different temperature when we would write a density for it? What's that?
What the temperature is?
Yep, we'd have no temperature, but how could we show something at, water at 100 degrees Celsius and compare it to water at 10 degrees Celsius? Are they going to be the same or different densities? Different. But when you take a look at density when we use it, we usually just use 1 gram per centimeter cubed to make it simple. So how could I represent this number better to show the difference between those two? So how many significant digits would be in this number that I'm relating? How many significant digits are there? 1. Okay? So how many do you think these would need in which to be able to tell the difference between them? Can we use 1 significant digit? We can't. So a lot of times water, when you take a look at water, it'll be like 0.9983 there. And then maybe 10 degrees Celsius, it'd be 0.9997. Can you see the difference in the densities? Okay. So you'd have to take it out further. You'd have to have more precise ways in which to measure the volume and mass in which to get to that detail. But you could have that detail. Okay. So we're going to do a couple problems. The first one, all of these, I'm just going to give you the problem, and I'm going to, the data is on page 55. So this is your background information on 55. Okay? And you know the equation. So I'm going to give you the first problem, and I want you to go ahead and solve for that problem. We're looking for volume of neon. And so, since I'm recording this, I'm going to go ahead and write the density of neon up here. You go ahead, I'm going to give you 2 minutes. To solve that problem. I want to find the volume of neon. Because in chemistry, your units never lie to you. If you're truthful on all your conversions, your answer won't lie to you. And so, like on this one, I think a lot of you were trying to say density is equal to mass over volume, and so you're having to solve for volume and isolate it. But I find it easier just to use factor label method. I'll go 12.5 grams. Some of you like to put the conversion out in front. Put the measurement out in front of neon, for example. Then down below, you're going to put grams, and up here you're going to put liters. And so you say for every 1 liter I have 0.902 grams. And then you get your answer. So look at your units. Say, just like in conversion, boom, liters, I got it. My final answer is liters. Is this truthful? Yeah. 0.902 grams I will have of neon if I have a sample of 1 liter of it. So that is truthful. And that's at 0 degrees Celsius. Okay? And this is at 0 degrees Celsius. So when you go ahead and do that, your answer, I think, comes up to be like 13 something. And I would, a lot of you, I think, can help yourselves out if you look at your answer and say, well, is that logical? And a lot of times you guys will do an answer and you go, oh, I'm just going to put it because I calculated it out and it must be right. But a lot of you might want to look and go, okay, does this make sense? For every 1 liter, I have 0.902 grams. So if I have 13 or 14 liters, will that come out to be about 12.5 grams? I got 14 liters, 14 times that. Yeah, that'd be about 12.5. So I think a lot of you can look at your data. Some of you might have taken 12.5 times 0.902. That doesn't get rid of your units of grams. Okay, what that gives you is grams squared over liters is your units if you did that. And your grams wouldn't cancel out. So I think there's about 5 of you that did a really good job of setting that up because you remembered units have to cancel. So I got a second one for you to do. This should be easier. This shouldn't take as long, so go ahead and calculate the mass of 30 milliliters of ethanol. So go ahead and do that. And I'm going to go ahead and put the density of ethanol up here. That one. Okay, so in this one, I put my 30 milliliters out in front. I know that for every 1 milliliter I have 0.79 grams. So down here I'll put 1 milliliter is equal to 0.79 grams. Milliliters cancel, my units are grams of ethanol. So then all you do is just multiply those two and you've got your mass. So correct number significant digits, you're not going to write 24, but you're going to write 23.7. Because there's 3 digits there. Okay? Right. So this is just like we've been doing with conversions. Centimeters to meters. Millimeters to meters. Okay? Feet to inches. Pounds to kilograms. That's all this is conversion ratio. Right? Last one's going to be a little tricky, but let's see if you can do it. Okay, so this one, it's a little bit of a twist in it, so I'm going to go ahead and have you do that one. This will be the last one we'll do. Pay attention to units, and I think I only had one person get this right in the last class. Okay, and so what you do is you go 50.2 grams of mercury. So down here goes grams of mercury, and up here goes milliliters or centimeters cubed of mercury, but it'd be milliliters. So down here I would put the density of mercury, and so mercury's density is 13.6. to 1 milliliter. So the question is, how many liters? So some of you stop there and you give an answer in milliliters. So what you would do is you'd go one more step and you'd say, for every how many milliliters, how many liters do I have? So when you look on your chart, it's milli. So that means for every 1 liter, you have 1 times 10 to the third, or 1,000. And then you get your answer. Okay? So when I say you have to be conscientious of units, that's what I mean. You can't just come up with an answer and without checking your units all the time, because it is important to have the units down correctly. And so the answer for this one would be 0.00369. Okay, so why would we want to have it in liters? I don't know. There's times when we have certain units we have to work with so we can compare. Yes, ma'am.
So confused.
Okay, what are you confused on?
Okay, so I get like